In our previous lessons, we were looking at finding the greatest common factors for polynomial expressions. So the greatest common factor means that every single term in the polynomial expression has that in common that we could divide out and see what remains. So here we have the polynomial x to the third plus 7x squared plus 2x plus 14. The question is, can we write this in factored form? So does a greatest common factor exist for all the terms of your polynomial other than 1? And as you look, 3 of the terms have an x in common, but not all 4. And if we look at some of the other values, we kind of see some patterns involved, but not a common factor with all 4 terms. So what we can do here is, because there's 4 terms, perhaps we can look at them in groups, in pairs, and see if there's a factor that exists within those. So again, with 4-term polynomials, we could try something that's called factored by grouping. We're going to split it into pairs and look at the first 2 terms and the last 2 terms as the groups, and see if we can divide out a common factor from each of those groupings. So again, the first grouping for our polynomial that we were looking at would be x to the third plus 7x squared. Both of these terms have x's in common. In fact, there are 2 x's that we could divide out from each term. So if I do that, I would have x squared times x plus 7. Now if I look at my second pairing in the polynomial, 2x plus 14, they both have a common factor of 2. So if I divide out the 2, I would have 2 parentheses x plus 7. Well, what do you know about these groupings? Each pairing has a factor of x plus 7, which again, we could divide out and see what's remaining. So if I'm dividing that out, I'm going to have my x plus 7 here, but what's left over? The x squared and the positive 2. So I can rewrite this in the factored form of x plus 7, which is what each pair had in common, and what was remaining? The x squared plus 2. And again, to double check and make sure this is correctly factored, we could take the x plus 7 times x squared and the x plus 7 times 2, and we'll end up back with the original polynomial, right? X to the third plus 7x squared plus 2x plus 14. And so that's our goal. Whenever we're factoring, we're still maintaining the value of the original polynomial expression, just writing it in its more basic components. So let's take a look at another example here. Here we have 24x to the third minus 6x squared plus 8x minus 2. We always want to look to see for the polynomial, does it have a greatest common factor across all 4 of the terms? If it does, we'll divide it out like we normally do and see what's left. In this case, all 4 terms do have a common factor. They all have a factor of 2 that we can divide. So what would be left? 12x to the third minus 3x squared plus 4x minus 1. So notice that these terms are a little bit smaller for the polynomial to work with. And because we have the 4 terms within those parentheses, we're going to say, well, can we break it down even more to those basic components? So look at them in pairs here. This 12x to the third minus 3x squared, do they have anything in common that we could divide out? How about that 4x minus 1? Do they have anything in common we can divide out? Well, this 12x to the third minus 3x squared, they both have a common factor of 3 and x squared we can divide out. So we would have our 2, our left parenthesis, keeping consistent from before. Then we'd have 3x squared, our parenthesis, what's remaining, 4x minus 1, close it with our right parenthesis. If we look at the second pairing, the 4x minus 1, well, they only have a greatest common factor of 1 to divide out, so we could leave it as 1 times 4x minus 1. And notice, with those pairings, they have that common factor of 4x minus 1. So what was in common with the polynomial? The 2, the 4x minus 1, and what remains? The 3x squared plus 1. So that would be our completed factored form. 2 times our quantity 4x minus 1 times the quantity 3x squared plus 1. And again, to make sure that it's equivalent to the original, we could take the 4x minus 1 times 3x squared times x plus 1, which would bring us back to this part here. Multiply everything by your 2, which brings you back to your original, and you know you're on target. So let's try this polynomial. Here we have 3x squared plus 6x plus 27 plus 54. And again, we're going to look at all four terms and ask ourselves, is there something in common we can divide out from each of those terms? And in fact, each of those terms have a 3 in common we could divide out. So what would we be left with then? X to the third plus 2x squared plus 9x plus 18. Because we have the four terms, again, we're going to look at it in groupings, in pairs. So we're going to split them into pairs. And this first pair, do they have anything in common that can divide out? Well, they have an x squared in common. So if we divide out the x squared, what would we be left with? X plus 2. Our second pairing, do they have anything in common that can divide out? In fact, they have a 9. So we'd have 9 parentheses x plus 2. And what do you notice about your pairings? They both have a factor of x plus 2. So the common factors so far are 3, x plus 2, and what remains? X squared plus 9. So that would be our completely factored form. Again, how would you check and make sure you're on target? Take the x plus 2 times x squared, take the x plus 2 times 9, it's bringing you back here, multiply them out, you're here then, distribute your 3, and you're back to your original polynomial. How about this polynomial? 6x to the third plus 3x squared plus 2x plus 1. Look at the polynomial and see, is there a greatest common factor across the four terms? There is not. Now we're going to look at it in pairs. The first pair on the left, 6x to the third plus 3x squared. Do they have any common factors that you can divide out? They have a 3 and an x squared. So we'd rewrite this as 3x squared parentheses, what remains? 2x plus 1, close your parentheses. Your second pairing, do they have any common factors that you can divide out? The only common factor they have in common is 1. So we're going to write 1, our left parenthesis, 2x plus 1, and close it with the right parenthesis. Well, what do you notice about your pairings? They both have that common factor of 2x plus 1. So if we bring that to the forefront, we've got 2x plus 1, and what remained? The 3x squared plus 1. That would be our factored form. How would you check and make sure this is correctly factored? Take 2x plus 1 times 3x squared, see what you get. Take 2x plus 1 times 1, see what you get. Combine your like terms. You should have your original polynomial, 6x to the third plus 3x squared plus 2x plus 1. How about this polynomial? 4x squared plus 20x minus 3xy minus 15. Again, scan the polynomial and see if there's a greatest common factor with all of the terms. And in this case, there is not. Then we want to see if we break it into pairs, do the pairs have any common factors we can divide out? Well, our pair on the left does have a common factor of 4 and an x. So if we rewrite this, we'd have 4x, left parenthesis, what's left over? X plus 5, close it with your right parenthesis. Now your second pairing, do they have anything in common that you could divide out? Yes, they do. They both have a -3 as well as a y. So we can write that as -3y, left parenthesis, what's left over? X plus 5. Well, what do you notice about your pairings? They both have a common factor of x plus 5. So if I divide that out, we've got x plus 5 and what remained? 4x minus 3y. How can you check and make sure you're on target? Take x plus 5 times 4x, see what you get. Take x plus 5 times -3. Take both of those results, combine your like terms, and it should bring you back to the original polynomial of 4x squared plus 20x minus 3xy minus 15y. Here we have a polynomial of 2ax squared plus bx squared minus 6ay squared minus 2by squared. The question is, can this be factored? And you look across the four terms and ask yourself, is there something that each of the terms have in common that you can divide out? And in this case, there isn't. So then we're going to take a look at it in pairs. And we ask ourselves, with the pairing on the left, do they have anything in common that we can divide out? And they do. They have an x squared. So we'd have x squared. Then our left parenthesis, what would be left over? 2a plus b. Then we look at the pairing on the right and ask ourselves, is there anything there that they have in common that we could divide out? Well, they both have a factor of -2 and a y squared. So we'd have -2 parentheses what's left over. 3a, what is it, plus b. Now we look to see what remains. And notice they're not the same for our pairing, right? So we don't have that common factor like we did in our previous examples. So can we continue on factoring? No, we can't. This is showing that it's not factorable from the original. Well, the question is, well, maybe it's not arranged correctly. Maybe we can rearrange it and try again. What if we arranged it so it was 2ax squared minus 6ayy squared plus bx squared minus 2by squared? There are still some common factors within these pairings. And so if I divide out those common factors, see what remains. And again, each pairing still does not have a common factor. So what does this tell us? This tells us that this polynomial is not factorable. And when that happens, we refer to it as prime. And that happens often with polynomials. Not every polynomial that you're working with can be factored. And again, we refer to those as prime. So today we reinforce the concept of having a greatest common factor across a polynomial, and as well as when we have 4 terms for our polynomials, if we can split them into pairings, seeing if the pair has a greatest common factor we can divide out to put the polynomial in factored form. That is what you're going to be doing for your practice for today's lesson.